We've seen the power of bisection when it comes to finding roots, in that the solution will always converge. But it is a bit of a brute force method, and in some instances can be inefficient. So if we plot our function on some set of axes, we've seen the power, as I've mentioned, that whenever we search between an interval for a root, we'll always converge on that root. But as I mentioned, the bisection method doesn't take into account the magnitude of the function at our lower point and our upper point. That is f of xl and f of xu, where xu is our upper bound and xl is our lower bound. For example, if we try to use some bisection method and it turns out that our lower bound, xl, the magnitude of f of xl, so if f of xl is quite a lot less than f of xu, we know that we must be, or sorry, it's f of xl is close to 0, then we know we must be near the root. And this might help us to come up with, to optimize our solution technique. So we can exploit this graphically. So if we join, this is f of x upper with f of x lower, can you see that we have now created a triangle? And the intersection, so we've joined f of xl with f of xu with a straight line, and the intersection is going to be our approximation of the root. And we can use similar triangles to calculate that position. So for example, if the ratio between f of xu over f of xl is going to be, remember this is what we're assuming our root to be, it's going to be xu minus xr over xr minus xl, which can then be rearranged to get that the position of our root is going to be our x upper minus function value of x upper multiplied by x lower minus x upper divided by f of xl minus f of x upper. Okay, let's explore this with some examples.